light makes a potential for atoms. If we take a two-little atom and shine resonant light on it, then we know that's going to have a very strong effect on the atom. It's going to excite it, it's going to give it momentum kicks whenever it absorbs a photon. When it emits a photon, it's going to get a momentum kick in a random direction, and it's going to be kicked around and change state a lot. If, however, we shine very highly detuned light on that transition, then on average it's not going to get very much excitation. There is still going to be an effect, though. If you look at the Hamiltonian for the two-little atom, you look at the Jaynes-Cummings Hamiltonian, when you shine very strong light on there, you're still going to get a significant change in energy in your dress states. And that change in energy corresponds to a phase shift on the light, or alternatively, it corresponds to a phase shift on the atoms. In other words, the light is acting just like a potential for the atoms. And it turns out that if you detune further and increase the intensity appropriately, you can get less scattering and increased potential. So that's really good news, because we can do a lot more with lasers and light in terms of spatial dependence and temporal dependence than we can do with magnetic fields. And one of the things we can do is we can shine our lasers from all directions. If we shine our lasers from one direction and the other direction, then of course what we're going to get is a standing wave. And that standing wave is going to produce a completely oscillatory periodic potential. And periodic potentials are incredibly good if you're trying to model things like condensed matter systems. And if we shine it from the other two directions as well, we can make a two-dimensional lattice. And if we shine it from three directions, we can make a three-dimensional lattice. And a three-dimensional lattice is a whole bunch of individual wells in a three-dimensional array. Now, if we have a bunch of neutral atoms in that potential, how do we model that? Well, we can make a good guess at the Hamiltonian, where we made the contact potential approximation there, and that potential in there will be this periodic potential from our lattice. But of course we don't want to deal with that system because that's too complicated. We want to try and reduce it to as few modes as possible. Now what's the very least number of modes we can deal with in this system if we're going to make it really cold? Well, the answer is at least we're going to have at least the ground state mode in each well. So if we look at this well on a very small scale near the center, so if we zoom into this center here, anything that's trapped like that is probably going to be harmonic, and indeed a sinusoid, if you look at the bottom of the well close enough, it's going to look harmonic. And so those are going to look a little bit like little harmonic oscillators, until you get too highly excited, in which case you'll start to see that the band structure is a little bit different. But our first guess is each of those modes is a fairly good choice for the kinds of modes that are going to be occupied. So let's give them annihilation operators. And our position-based field operator is going to be some superposition of these. So obviously there'll be a larger superposition because we haven't included all the modes, but the idea is all those other modes are supposed to be fairly empty and so they shouldn't turn up. So now we have to find the Hamiltonian. Now the Hamiltonian is going to be exactly what it is up here, and we could just substitute these things in if we happen to know those wave functions, but we're going to do a bit of approximating now. So basically these wave functions are going to be more or less Gaussians stuck on their well site like that. And they're going to be, because they're the ground state energies of those wells, they're going to be pretty close to eigenstates of that. And so where we're going to set the zero of energy, let's set the zero of energy to exactly there, and therefore all those terms will be zero. So the energy eigenstates will be there, but that energy eigenvalue we can just set to zero. So that's done. What's the next effect? The next effect is all of these things are going to have some coupling with each other. But of course, this one is going to have some coupling with its nearest neighbor due to the wave function overlap, but it's going to have very little coupling at a distance. So these two are going to be almost entirely uncoupled because their wave functions are not going to overlap at all. So what that means is that the dominant term here is going to be the nearest neighbor coupling, and I'm just going to give it a constant J. And so there's coupling from nearest neighbors. So you might delete a particle from here and create one over here or vice versa. And that covers all of this term, but what about the nonlinear term? Well, that nonlinear term, once we expand all of these wave functions in, we're going to get, as our dominant term, we're going to get the a dagger squared a squared terms. And then for all the terms where the k's are different, where we have different indices between our different a's and our a daggers, we're going to have quartic wave function overlaps. And if those wave functions are well localized, then those are going to be really, really small. So our dominant term is just going to be the local terms. And the reason we've gone for this n-1 form rather than the 8 squared a squared form is I wanted to set the zero of the energy such that if you have precisely one particle in each well, then you don't have any nonlinear terms. In other words, one particle doesn't really interact with itself. But if you have two particles, then we'll have u amount of interaction energy between them, and then from then on, as you have n particles, it goes up as n squared. Now this is a very famous model called the Bose-Hubbard model. And one of the reasons this is a famous model, besides the fact that bosons in a periodic lattice is a fairly common kind of physical occurrence, is that it has a phase transition in its ground state. So let's think about what the ground state is. So we've got two regimes. The first where J is much bigger than U. In other words, that's when the nonlinear terms are really small. And what we really have is just a whole bunch of connected modes. And in that mode, it works just like a BEC did when we didn't have the lattice on. And so that's called the superfluid mode. In that regime, if we were to do an interference experiment between these different wells, then we'd expect to see some kind of phase coherence between them. And the other limit, of course, is where the nonlinear terms are really large. When that nonlinear term is dominant and the energy of each well goes up as n squared, it's not too hard to figure out what the ground state should look like.